In this session, we will discuss the conversion of decimal number to its equivalent binary value. Now, in the decimal number system, we have seen that the symbols that are used are 0, 1, 2, 3 up to 9. And since there are 10 symbols, we say that the base or radix of decimal number system is 10. In the binary number system, only two symbols 0 and 1 are used, and so we say that the base or radix of the binary number system is 2. The binary number system does not use symbols like 2, 3, 4, etc., and therefore those are not valid in the binary number system. Let us understand what is meant by LSD and MSD in a decimal number system. LSD stands for least significant digit and MSD stands for most significant digit. To understand this topic, let us consider a decimal number 572. There are three digits 5, 7 and 2. Now this number 572 can be written as 500, which is the first part, then plus 70 and plus 2. Now 500, we are writing it as 5 times 100. In fact, that is why we pronounce it as 500. It is as if it is 5 hundreds. Plus 70, we are breaking it up as 7 into 10, so it is 7 times 10, and plus 2, we write it as 2 into 1. So from our school mathematics, we will remember that we say that this number 2 is in the units place. So we say that 2 is in units place, and the reason for that is that it is multiplied with 1. But the number 5 in this particular example is in hundreds place because it is multiplied with 100. So this is our value 572. Now you will observe that this has been written as 5 times 100 and plus 7 times 10 plus 2 times 1, and here the digit 5 is multiplied with 100, which in powers of 10 we can say it is multiplied with 10 raised to 2. Similarly, digit 7 is multiplied with 10 raised to 1, and digit 2 is multiplied with 1, and that 1 can be written as 10 raised to the power 0, since we know that any number raised to 0 is 1. Now 5 is multiplied with the highest weight here, and that is 100, and therefore we say that 5 is the most significant digit. And if you look at the digit 2, 2 is multiplied with the lowest weight of 1, which is also 10 raised to 0, and we say that the least significant digit is 2. So in this number 572, 5 becomes the most significant digit. It is a digit with the highest weight, whereas 2 has a weight of only 1. So we say that this number is a positional numbering system because if we change the position of any digit, then the value of that number changes. So in a positional numbering system, the position of a digit decides the value of that digit. Now let us take an example to convert a decimal number to its equivalent binary value. The method is outlined here, and as we go through this one step at a time, we will see how to convert this number 23, which is in the decimal system, to its equivalent binary value. So we have made here three columns, and in these three columns, in the first column we will write down the multipliers, that means 2, the divisors 2. Then we have the number that we want to divide. This number appears in the central column. This is the number that has to be converted, and in the last column we will write down the remainders, and these remainders will give us the bits of the binary number. So we'll start by first dividing the decimal number 2 by 2, and therefore I'll write here divisor as 2. 2 now goes 11 times in 23, so 2 11 times 22, and that leaves us with a remainder of 1. So we have these three steps. So we got the remainder 2 11s are 22 and the remainder is 1. Now in the next step, we will continue with division of this quotient by 2, and we'll continue this till the quotient becomes 0. So now we will just take this 11 as our quotient and divide it by 2. So again 2 5 times is 10, that leaves us a remainder of 1. Since this quotient is not yet 0, we will again divide this by 2. 2 times is 4, that leaves us with a remainder of 1. Now 2 again divided by 2, because this is not yet 0, so 2 1 times is 2, that leaves us with no remainder, so we write 0 as the remainder. This quotient is still not 1, it is still not 0, and therefore we again divide this by 2. So 2 0 times is 0, and that leaves us with a remainder of 1. Now you can observe that the quotient has become 0, so we will now consider the remainders in the reverse order, and our binary equivalent becomes 1. This becomes the most significant bit, then 0, that is our next bit here, then 1 1 and 1. So those are the three remaining bits, and this becomes the binary equivalent. Now when we pronounce this, or when we read this, we read it as 1 0 1 1 1. Now that we have seen what is LSD and MSD for a decimal number, we also have what are called as the LSB and the MSB of a binary number. Let us consider the number 10111. This is a binary number which we obtained in the previous example. This number has 5 bits. These are the 5 bits of that number, 1 0 1 1 1. Now out of these 5 bits, the bit which is at the extreme left, that means the bit 1, this bit is called as the most significant bit. This is similar to the most significant digit, which was the digit at the extreme left of our number. The right bit, the rightmost bit, which is in this case 1, this rightmost bit we will call it as the least significant bit. Now observe this. What is the significance of these terms, most significant bit and least significant bit? A change in the least significant bit will not change the value of the original number drastically. The bit can be either 0 or 1. So let us assume that our original number is 10111. The decimal value of this number is 23. If we change the least significant bit from 1 to 0, we get the number 1011, and here is the bit which was originally 1 in our number. Now we have changed it to 0. Now if we convert this number from binary to decimal, we get the decimal equivalent as 22. So by changing the least significant bit, the value has changed from 23 to 22. It's not a very significant change. But observe what happens if we change the most significant bit from 1 to 0. Again, here is our original number 10111. If the most significant bit is changed from 1 to 0, in the original this was 1, if it is changed to 0, and we keep the other bits as they are in the original, so the other bits remain there same, and now if we convert this into the decimal equivalent, this gives us the decimal value 7. There you can see there is a drastic change in the value of the number, and therefore the most significant bit has the significance that its value decides the value of the number. If this value changes from 1 to 0 or 0 to 1, the final number can change drastically. Now in this example 2, let us consider the conversion of a decimal number to its binary equivalent, and we'll use another method. So in this method, we will first write down all the powers of 2, and we'll start from the power of 2, 2 raised to 0, and we'll keep on writing the powers of 2 from right to left. So 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, and we will come up to 2 raised to 7. Now below that we will write the values of these powers. So 2 raised to 0 is 1, 2 raised to 1 is 2, 2 raised to 2 is 4, and till we reach here 2 raised to 7, which is 128. Now these powers of 2 are actually simple to calculate. Just we need to remember that 2 raised to 0 is 1, and from here on we just keep on multiplying each of the values 1 multiplied by 2. So 1 into 2 gives us 2. Then we multiply this 2 again by 2 to give us 4. Again multiply this 4 by 2, so that gives us 8. 8 into 2, 16. 16 2 times 32. 32 2 times 64. And 64 2 times is 128. So it's very easy to get these values. Now let us understand how do we fill up the values in these cells for the binary digits. We start with our number 73. We will compare this 73 with the value 128. If the value 73 is less than the value given here, we will put a 0 in the binary digit cell. Again we compare 73 with the number 64. 73 is greater than 64, so we'll write a 1 bit, and 73 minus 64 gives us 9. Now we will compare 9 with 32. So now our comparison is of 9 with 32. So 9 is less than 32, so we put a 0. Now we compare 9 with 16. So 9 is less than 16, so put a 0. Again we compare 9 with 8. So 9 is greater than 8, so we put a bit 1. And now the value that we have is 9 minus 8, which is 1. So now we compare 1 with the next value. So 1 will be compared with the value 4. 1 is less than 4, so we put a 0 bit here. 1 we compare it now with 2. 1 is less than 2, so we put the bit 0. Now we compare this one with 1. 1 is equal to 1, so we put the bit 1, and therefore now we have reached the value 1 minus this value 1, which is equal to 0. And now we consider these bits, binary digits, in the forward order, and therefore our binary number becomes 0101. This is the first part which we have considered. So all these values 0101, 0100, followed by 1001. Those are the values that we have obtained here as our binary number. And when we read this number, we read it as 01001001. Let us now understand how to convert a fractional value to the binary value. Let us, as an example, take the fractional number 0.3125. This is a decimal number with 4 decimal places. This has to be converted into the binary. Now, the method is outlined here in the box. So the method is, we will keep on multiplying the given number with 2. So multiply the fractional part by the decimal number by the number 2. So in the first part, we will take 0.3125 multiplied by 2. This gives us the value 0.6250, and because there is no carry, we write the carry as 0. So when you multiply 0.3125 multiplied with 2 gives us 0.6250. Since there is no carry, we write here. Then we take this fractional value and use it as our next number. So we have as if taken this fractional value, and now we will again multiply it by 2. Now observe this part. 0.6250 into 2 will give 1.2500. So the 1 we write it as a carry, and fractional value becomes 0.2500. So we will again continue this 0.2500. This part has been brought forward, and now multiply this by 2, so that will give us 0.500. When you carry out this multiplication, there is no carry, and therefore we will write here a carry of 0. Now we will take 0.500 again, we will copy it into the number column. So 0.500 multiplied by 2 will give us 0.0000 with a carry of 1. And now these carries, we consider them in the forward order, and therefore our decimal value 0.3125 is equivalent to 0. So you have 0, 1, 0, 1. Those are the 4 bits. This point that we have here is called as a binary point. We will call this as a binary point because it is a part of a binary number. This is of course analogous to the point that you have here. We call this as a decimal point because it is a part of a decimal number. Now, let us consider how to convert a mixed number like 23.3125 to its binary equivalent. Now, this 23.3125, you can see, has been broken up into two parts, an integral part 23 and a fractional part of 0.3125. So, the first part of converting this number 23.3125, converting it into binary, will involve two steps. In step 1, we will convert the integral part 23 to its binary equivalent. This we have seen in the earlier case, 23 of decimal. We saw in the earlier example is 10111 of binary. In step 2, we will convert the fractional part 0.3125 to its binary equivalent. So that was 0.3125 is 0.0101, and therefore our final answer 23.3125 will consist of the binary equivalent of 23, which is 10111. We got that value here, followed by the binary point, and then 0.3125, it has the binary equivalent of 0.01.0101. So that is the one value we have shown, and therefore this is the complete answer for 23.3125. In this video lecture, we will see how to convert a binary number to its decimal equivalent. Let us take the first example in which we have to convert the number 10111 from binary to its decimal equivalent. Now the first step in doing this conversion is to identify the least significant bit and the most significant bit. So our given number is 10111. Now the rightmost bit is the least significant bit because it has the smallest weight. The bit at the extreme left, that is this one, is our most significant bit because it has the highest weight. Now, having done this, we will first make a table of 3 rows. Our first row contains the powers of 2. Here, we have started from the right. We start with the powers of 2. So 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, and we go up to 2 raised to 7. Now, for this particular problem, we will not require up to 2 raised to 7, but this is a general explanation which can be used for any problem which involves up to 8 bits. Now, in the next row, we write down the values of these powers of 2. So 2 raised to 0 we know is 1, 2 raised to 1 is 2, 2 raised to 2, 4, 2 raised to 3, 8, and like this, we have 2 raised to 7 is 128. Now, the third row, we will have the bits. Now, let us observe how to fill up this bits row. Starting from the least significant bit, we will start from the least significant bit, and that is why this has been highlighted here. What we will do is, we will write each bit below the corresponding power of 2. So, as we said, this is the least significant bit which has the smallest weight. So, we will write this bit under the power of 2, that is 2 raised to 0. So we bring this bit here 1. The next bit in our number is 1. This is the bit with the next higher power, and therefore we now bring this bit to 2 raised to 1, that is 1. The next bit is again 1, that is copied under 2 raised to 2, that is the value 4. So this bit has the weight of 4. The next bit in our number is 0, which is written under 2 raised to 3. That means the value of this bit or the weight of this bit is 8. So we write 0. And the most significant bit, we put it here under 2 raised to 4, that is 16. So all our bits have been copied, and since there are no more bits left, we will just pad these remaining powers of 2 with zeros. Now all the bit positions have been allotted, and so our given binary number can be written as 0 into 128. Now this 0 is the bit at the extreme left. This we multiply it with 128. So this is 0 into 128. Then similarly 0 into 64. This is 0 multiplied by 64. That gives us the next. Then 0 into 32. 0 into 32. Then plus 1 into 16. So we have the bit 1 multiplied by its weight 16. 0 into the weight 8. 0 into the weight 8. So at each position what we are doing is we are multiplying the bit, that is say this bit, with the appropriate power of 2 or the value. So 1 into 4, so that is 1 into 4. Then we have the next bit 1 into 2, so 1 into 2. And the last bit is 1, we multiply it by its weight 1, so that is 1 into 1. And therefore this becomes 0 into 128, that is 0, plus 0 into 64, 0. And like this we have 1 into 16, you can observe, is 16. 1 into 4 is 4. And therefore we have the given binary number as a sum of these values, and this can be written as 0001, 0111 of binary is equivalent to 223 of the decimal. So these three zeros that we see here at the extreme left, these have been padded to create an 8-bit binary number. So these were not really necessary, but in case we come across an example where 8 bits have to be used, then we know that we must go up to 2 raised to 7. Let us take the next example where we are to convert the binary number 10010 to its decimal equivalent. Again, the steps will be similar. First, we identify the least significant bit. So 10010, this becomes the least significant bit, the bit which is at the extreme right. So this is the bit which is at the right, and we have the most significant bit, that is the bit at the left. So we have identified the bits. Again, as in the previous example, we make a table of 3 rows. The first row is powers of 2. So starting from the right, we have the powers of 2, 2 raised to 0, 2 raised to 1, 2 raised to 2, and like this we go up to 2 raised to 7. Below that, in the next row, we write down the values of these powers. So 2 raised to 0 is 1, 2 raised to 1 is 2, 2 raised to 2 is 4, 2 raised to 3 is 8, and so we have up to this 2 raised to 7 is 128. Now again in this, the third row will contain the bits. So we will pick up each bit starting from the least significant bit and put it below the appropriate power of 2. So since this is the least significant bit, it has the smallest weight, we copy this bit under 2 raised to 0, so that is 0. The next bit is 1, so we copy this bit under the power of 2 raised to 1. Our next bit is 0, that will be copied under the power of 2 raised to 2, that is the value 4. The next bit I have here is 0, so we copy it under the power 2 raised to 3 with value 8. And the last bit, the most significant bit in this example, is 1, so that is copied under 2 raised to 4, and that becomes 1. Since all the bits have been used up, we just pad the remaining bits with 0. And again, in this example, our number is 0001 0010. It's the same number, but we have padded these 3 extra bits. These are the 3 extra bits. So you have 000, that explains these 3 bits, followed by 10010. Those are the remaining bits. This is equivalent to, now let us see, we again multiply each bit with the corresponding value. So 0 into 128 plus, we'll have 0 into 64 plus, we have 0 into 32 plus 1 into 16 plus 0 into 8 plus 0 into 4 plus 1 into 2 plus the 0 into 1. So we are multiplying each bit with the appropriate power of 2, and this can be written as 0 into 128 is 0, 0 into 64 0, 0 into 32 0, 1 into 16 is 16, plus 0 into 8 is 0, plus 0 into 4 is 0, plus 1 into 2 is 2, and plus 0 into 1 is 0, and this is equivalent to 18 of decimal. So this is how we can convert a given binary number to its decimal equivalent. Now, here is an important observation about binary numbers. Let us take the examples we solved earlier. This was the first example, 10111, and we saw that its decimal equivalent is 23. The next example was 10010, and its decimal equivalent was 18. Now observe this. In the first example, the least significant bit was 1, and the equivalent decimal number was an odd integer. So we have an important result. If the least significant bit of your binary number is 1, then the equivalent decimal value will be an odd integer. Let us take the next example where our binary number was 10010. Here the least significant bit was 0. The binary equivalent, the decimal equivalent of this was an even number, and therefore here is our result. If least significant bit is 0, then the equivalent decimal value is an even integer. Now this, you will realize, is somewhat similar to what happens in the decimal numbers. We know that any number which ends with 0, 2, 4, 6 or 8 is an even number. So for example, number like 12, 16 or maybe 24, 18, 30, all numbers ending with 2, 4, 6, 8 or 0 we say are even numbers. And if a number ends with 1, 3, 5, 7 or 9, is we say it's an odd number. So we'll have numbers like say 23 or 31, 45, 67 or 89. All such numbers we say are odd numbers. So in a similar way, the important result is numbers, binary numbers in which the least significant bit is 1, we say that the equivalent decimal value will be an odd integer. And if the binary number has the least significant bit as 0, then we'll say that the equivalent decimal value is an even integer. Now this result is important, and it can be sometimes used to check our answer when we convert from a binary to decimal or from a decimal to binary. Let us now take up an example of what happens with fractional binary numbers, fractional decimal numbers which have a value less than 10. Now let us consider a number such as 0.142 in the decimal system. Now this number can be broken up as a sum of 3 parts. So we have 0.1 plus 0.04 plus 0.02. So we can see that this can be broken up into 0.1 plus 0.04 plus 0.002. Now this part can be written as 0.142 can be written as 1 upon 10. So 0.1 is 1 upon 10. 0.04 can be written as 4 upon 100, and 0.002 can be written as 2 upon 1000. That means we can write 0.142 as 1 into 10 raised to minus 1. So you have 1 upon 10. When the 10 is taken up in the numerator, we have 1 into 10 raised to the power minus 1 plus 4 into the power 10 raised to minus 2 plus 2 into the power 10 raised to minus 3. So the important result here is that any number less than 1 can be written as a sum of the products of the digit and the appropriate multiplier of 10. So since this is the first place, 1 into 10 raised to minus 1. Since 4 appears in the second place after the decimal point, we have 4 into 10 raised to minus 2. Since 2 appears in the third place after the decimal point, we have 2 into 10 raised to the power minus 3. Now this result we will use it when we convert a fractional binary number to its decimal equivalent. Let us take this example of converting the binary number 0.1101 to its decimal equivalent. Now, just as in the previous case where we were dealing with decimal number, we can write 0.1101 as 1 into 2 raised to minus 1. Why we take 2 raised to minus 1? Because since we are dealing with the binary number system, this will become 1 multiplied by the base of this number system is 2. So 2 into 2 raised to minus 1, because this is the first decimal place. Then we have plus 1 into 2 raised to minus 2. So why 2 raised to minus 2 we take here? Because this 1 appears in the second position after the decimal place. So 1 into 2 raised to minus 2. The next digit we have here, the next bit we have here is 0. So this will become 0 into 2 raised to minus 3. The next bit that we have here is a 1. So we have 1 into 2 raised to the power minus 4. And therefore, now this example is dealing with the fractional values of a binary number. Now we can observe one thing, that this 0.1101, if we write this number, then this 0.1, the bit 1 here becomes the most significant bit, whereas the bit 1 here is the least significant bit. And therefore we now again make the table of powers of 2, the value and the bit. Only now the difference is when we make the power of 2, as we go from left to right, the powers of 2 keep on decreasing. So we have 2 raised to minus 1, 2 raised to minus 2, 2 raised to minus 3, 2 raised to minus 4, and so till we have 2 raised to minus 7. The values of these powers, 2 raised to minus 1 is 0.5, 2 raised to minus 2 is 0.25, 2 raised to minus 3 is 0.125, etc. till we have 2 raised to minus 7. Now let us observe. We take each bit from our fractional number. So starting from the most significant bit, we put the bit under the appropriate power of 2. So we have 0.1, so the bit is 1. So we put the bit 1 under the power of 2 raised to minus 1. The next bit is 1. This bit is written under the power of 2 raised to minus 2. The next bit, that means the bit in the third position after the decimal point, we put it as under the power of 2 raised to minus 3. The fourth bit after the decimal point, we put it under the power of 2 raised to minus 4. And since there are no more bits, we just put these bit positions as we put these bit values as 0. And therefore our given number 0.1101 can be written as equal to 1 into 2 raised to minus 1 plus 1 into 2 raised to minus 2 plus 0 into 2 raised to minus 3, here it is, we can see this, plus 1 into 2 raised to minus 4, etc. And therefore this can be written as equal to 1 into 2 raised to minus 1 is 0.5, so 1 into 0.5 plus 1 into 0.25 plus 0 into 0.125 is 0 plus 1 into 0.0625 0.0625, and this 0 into 0.03125 0 plus the next number also will be 0, and the last 0 into this also gives us 0, and when we add this we get 0.5 plus 0.25 plus 0.0625, that gives us 0.8125, and therefore the given decimal number in binary can be written as 0.8125 of the decimal system. Now let us see how to convert a binary number like 10.1101 to its decimal equivalent. We'll observe that this binary number has an integer part, that is before the decimal, so it has an integer part, and it also has a fractional part, or it has also got a part after the binary point. So this we can say is its fractional part after the binary point. Now to convert this type of a number into its decimal equivalent, we first take the integer part, that means the part before the binary point, and we convert this number into its equivalent decimal. So this we already seen in the first example, how we convert an integral binary number into its decimal equivalent. Then we take the fractional part 0.1101. So we have the fractional part, or the part after the decimal, after the binary point, and we convert it into its equivalent decimal. So we saw in the earlier example that this is 0.8125, and therefore the entire number can be written as the integer part, which corresponds to 23, and then the fractional part of binary corresponds to 0.8125. This becomes our complete equivalent value in the decimal system.